Welcome. So Natalie is joining us from Baltimore, and she's going to introduce herself and tell us all about herself, and then talk to us about exoplanets. So take it away, Natalie.
Awesome. Thank you. Can you see these slides okay? And hear me okay?
Yes, yes.
Cool. So hi everyone. I'm Natalie. I am from Bainbridge, and so I'm very excited to be talking to all of you on Bainbridge who are interested in astronomy. So a little bit about myself at the moment. I just started the second year of my PhD at Johns Hopkins University as a National Science Foundation Graduate Research Fellow. Here I work with scientists on exoplanet observation, both here at Johns Hopkins as well as the very convenient across the street Space Telescope Science Institute. In particular, we are looking at exoplanet atmospheres. So to start off, here's just a short overview of what I'm going to be talking about. And we're going to start with some background, both about myself and about exoplanets. So after I graduated from Bainbridge High School in 2016, I attended the University of Rochester in upstate New York, a beautiful place with lots of research, lots of fun. So while I was there, I was able to be part of a lot of fun physics things. I was able to create a group of women in physics and astronomy, which was a big fun thing. I got to do a lot of astronomy outreach, a lot of fun things. And while I was there, and one of the reasons that I chose the University of Rochester was because they emphasized research starting really early. So while I was there, before I got into exoplanets, I did research in a few other things. I started research my freshman year and worked throughout all of my undergrad on star formation. So I looked at stars that were currently forming and looked at the effect that they had in the environment around them and what that could tell us about the whole process. I worked with Dan Watson, was able to publish some work, go to a lot of conferences, spread a lot of ideas, and I really enjoyed learning about astronomical observation. That's kind of how I chose that I wanted to do this sort of work. Um, I also did a work with Professor Miki Nakajima on simulating the formation of Earth's largest impact crater, which is the Vredefort crater in South Africa. It was formed about 2 billion years ago and is about 300 kilometers in radius. Very massive crater. This was kind of away from my normal interests because it was planetary science, but I really enjoyed working on planet scale things. Working on astronomy can sometimes be difficult at these very large scales, these very large ideas. And so I really enjoyed working on these closer to home techniques. But neither of these things really was like, this is what I want to do for the rest of my life until I got to go to NASA's Jet Propulsion Laboratory following my junior year for a summer internship. JPL is an amazing place. It's kind of like Disneyland for scientists, I would say. There's just so much science going on. A lot of the really famous missions, like for example, the Mars 2020 rover, which is now called Perseverance, was being finished the summer that I was there. So I was able to see it in the clean room before it went off to Mars. But while I was at JPL, I interned in an office called the Exoplanet Exploration Office. This is NASA's office that is in charge of determining where the field of exoplanets will go in the foreseeable future. The thing I think the office is probably most famous for in the general public is making these exoplanet travel bureau posters, where they kind of had this idea that, oh, we can make like kind of old-fashioned tourism bureau posters, but for exoplanets. You can see I literally have them on the wall behind me. They're a very popular thing for astronomers to have. But while I was interning in this office, I loved the field of exoplanets so much. There's so much happening that I decided that this is what I wanted to do with my life. So I decided to get my PhD studying exoplanet atmospheres. So to start from the very beginning, what are exoplanets? So exoplanets are planets around suns, stars that are not our own. And this is by far the most recent field of astronomy. That's kind of weird to say because one of the things that astronomers really pride ourselves on is that this field has been around for a long time, for essentially forever. It's kind of a joke that a lot of people will try in their thesis, will try to cite the earliest possible paper that they can. So we cite stuff from like ancient Greek astronomers, ancient Egyptian astronomers, etc. But on the complete opposite side, my friend Jacob, who's in my PhD program with me, was born on the day the first exoplanet was discovered. So the current generation of graduate students are exactly as old as this entire field. Shown here is the front page of the New York Times on October 6th, 1995. And you can see down here at the bottom, possible planet found beyond solar system. This planet was 51 Pegasi b, called 51 Peg. And the scientists who discovered this planet were awarded the Nobel Prize in Physics in 2019 for discovering this entire new subfield. We had to share it with the cosmologists because the Nobel Prize Committee in Physics doesn't like giving the prize to astronomers, but we're glad we have it anyways. So this subfield is very new because, as we will get to, it's very difficult to get these sorts of signals, but the ideas of exoplanets have been around for really most of recorded human history. Epicurus, who is a very famous Greek philosopher, is quoted as saying there are infinite worlds, both like and unlike this world of ours. He was basing this on atomic theory because this was kind of when the idea of atoms were being created. But he said this in around the year 300 BC. So we've been thinking about planets in other places for a long time, but this was not the dominant idea. In fact, Aristotle is very well known as not thinking that there are planets outside of the solar system. And as most people are aware, through a lot of history due to the influence of the Catholic Church, the geocentric model was very much preferred. So if we kind of move forward to that dominant period, here's some quotes from some famous astronomers, including Giordano Bruno, who had this idea of countless suns and countless earths and was burned at the stake for heresy for this idea. So that was not great. But similarly, Christian Huygens, who is a very famous old astronomer, had similar ideas around why would our sun be special? Why would we not see planets around other stars? So we've had these ideas for a long time. Starting in 1995, we were able to finally see them. So where are we today? As of, I literally went on the Exoplanet archive this morning. They haven't updated it since Thursday, but as of this week, there are 4,500 confirmed exoplanets, at least. What I'm showing here in the plots is just kind of to give you an idea of all the different planets we know of. They span a bunch of different parameters. So we have orbital period on the x-axis in both plots, but on the left is planet mass, and on the right is planet radius. Also shown here is a lot of solar system planets, just to kind of give you an idea of the parameter space we're looking in. And I can't give a talk about exoplanet observation without talking about one mission in particular, which is already kind of spoiled here in the teal, the Kepler mission. So just to kind of give you an idea of how important this mission was, this is the known exoplanets before Kepler, and this is the known exoplanets after Kepler. All of the dots in yellow are all planets that were found by the Kepler mission. Kepler, one telescope mission, really revolutionized our ideas of understanding our place in the universe. It's a really amazing mission. It was in space for less than 10 years. Here it shows that there are 2 missions completed. That's actually because the first mission kind of failed. It had some gyroscopes that failed, which is a relatively common thing that happens with space telescopes. But the amazing engineers who were involved in this project were able to use the force from the solar radiation to point the telescope instead. So the mission was able to continue. A really amazing feat of engineering. So over its 10-year run, at least 2,500 planets were confirmed. This was in 2018. Planets are still being discovered to this day, even though the mission is no longer observing, because there's so much data that's coming out. A paper was actually published earlier this week that there is 400 new planet candidates in the data set, so expect more every day. And I just think it's a fun fact that in all of this, only 3 gallons of fuel were used. So we are pretty good at being fuel efficient as astronomers. Okay, so that's kind of some history of the field. But how do we find all of these planets? We have these telescopes, but what are the techniques that we're using to actually discover them, and what can we learn about? Um, so to start off, I'm going to talk about the transit technique, which is the dominant technique that we use to discover exoplanets, period. Over 3,000 exoplanets have been discovered using this technique. It's pretty easy to understand. Basically, as long as the geometry is right, as long as it is an edge-on system, as the planet orbits its host star, it will pass in front of the star, and in doing so, will block out some of the brightness. You can see that it also will block out, there's a little bit of a dip as the the planet goes behind the star. That has to do with temperature differences. But as it goes in front of the star, it will block out some area, and that area is exactly related to the ratio of the area between the planet and the star. So as long as we know how big the sun is, the star is, we know how big the planet is. So this gives us planet size. It also gives us planet atmosphere, which I will get into in lots of detail in a little while. But this is a really amazing technique. One of the downsides of it, though, is that it's very biased. In order for a planet to be confirmed, it has to have transited 3 times, which means that we are very biased towards things on close-in orbit, so things that orbit really often. And we are also very biased towards large planets because their signal that they block out is a lot larger. Because in this movie, it seems like this is a big dip, but most of the time it's pretty small. If you think about the size of a star in comparison to the size of a planet, there's a pretty significant difference. So really with the technology we have right now, in all but very specific cases, we're finding giant planets. Oh, I just want to show here that that looks really simple as well, but in reality, it tends to be quite a bit more complex, especially when you get into systems with multiple transiting planets. This is kind of more realistically what the data looks like. The next technique we're going to talk about is radial velocity. So if you think back to like your basic physics, you'll remember that when there's an orbiting body, they're not actually orbiting the central body, they're orbiting the center of mass of the system. What that means in most contexts is just it's orbiting the star. But really, in reality, there's a little wiggle that's going on in the star, even in the very small circumstances. And here, it's kind of exaggerated, and you can see that there's kind of this dance going on where they're kind of centered around the very center here, but that means the star and the planet are both moving. And so this causes shifts in the spectra, which I will get into what exactly a spectra is in a little while. But we're able to use this to determine the mass of the planet. This is the second largest technique. So the last one had order of like 3,000 planets that have been discovered. This one has around 850, I think, currently. This is also how the first exoplanet was discovered. So 51 Peg that I was talking about was discovered using this radial velocity technique. But a big similar problems to the last technique, it likes close-in planets, it likes large planets. And so we're not finding some very interesting candidates with our current technology. But one big thing is that if we use the last technique and this technique together, we're able to get the size of the planet and the mass of the planet, and that gives us the density. And using the density, we're able to determine in things like internal structure and composition, which is really important when we're trying to kind of dig into the details. To get into a very different technique, I'm gonna keep this one pretty short, but there is a technique called microlensing, which relies on the theory of general relativity. In the simplest terms, the idea is that general relativity says that objects with mass distort space-time relative to that mass. And so what's happening is a planet is passing in front of a star, and as that happens, it's creating a lens, which causes images of the stars behind them to form. And as that happens, the flux of this observation will increase. This is a weird technique. It tells us a lot of information. And the big thing is that it's the most unbiased sample that we can have. These are completely random how we find these objects. They're just random geometries that end up working out. And so we get a completely unbiased sample. The problem with it is that because it's just these random geometric configurations, we will never see these objects again. So we see them once and then they disappear into the void forever. So we know of some really interesting microlensed planets, but we can never look at them again. We actually have a planet candidate in Andromeda, so in another galaxy that was observed using this microlensing period, maybe, but we can't find it. So we'll never know, but it's cool nonetheless. On the other hand, the final technique I'll talk about is kind of the one that makes the most sense when you're first looking at it. It's this technique called direct imaging. So literally, we are directly imaging the planets. This example that I'm showing is by far the most famous of these systems. It's HDR 8799. And what you're seeing is the dates being shown on here. So over the course of a few years, you're actually seeing planets move around their central star. This is insane. I know it looks quite simple, but it's very difficult in reality, mostly due to the fact that stars are super bright and planets are not. The thing that people who do direct imaging always say is, imagine you're in New York City and in Los Angeles, there is a spotlight, and next to the spotlight, there is a single firefly. And you have some binoculars and you're trying to see the firefly. And even that is about a factor of 100 easier than how this actually is. But even though it's super difficult, we have techniques to deal with it. This system is using something called a coronagraph, which blocks out the central light. There's also this idea for something called a star shade. That's kind of a similar idea. And a big thing with this technique is that NASA sees this as kind of the future of the field. When I was working in that exoplanet office, they were basically writing a report that I will talk about quite a bit at the end of this, that said, this is the future. This is how we're gonna find these really, really cool objects. Yeah, so that is how we observe exoplanets generally. There's a few other weird techniques that are kind of one-offs, but this is a majority. Oh, I didn't say, with microlensing, I think we have around 100 planets that we've discovered, direct imaging about 50. So it falls off pretty rapidly. But through all this, we know of at least 4,500 exoplanets. With the TESS mission, which is currently observing, we have thousands more candidates. So there's lots of exciting news on the horizon. But with that, let's get into what exactly I do with exoplanets. So to do that, I'm going to describe a technique called transmission spectroscopy. We're gonna talk about it in a little bit of detail, but with some of this, you're just gonna have to trust me on because I don't want to lecture you guys on things that you might get bored of. But for basic sake, when I was talking about this transit technique before, this is literally just you point a camera at a star, you look at how the amount of light changes. You can do it with any telescope. In fact, if people here are interested in civilian science, there's a lot of really awesome exoplanet programs that NASA runs that civilian scientists can help with these exoplanet observations from their backyards. It's a really awesome program. But if we want to go kind of one step further in complexity, we move on to an idea called spectroscopy. And so what we do in this technique is we look at the light curve. So we look at the planet going in front of the star as a function of wavelength. So not just all of the light. Instead, we look at it in very set bins. And this changes the size of a planet in a very interesting way. So I'm going to run through this pretty fast, but if anyone is interested, Space Telescope Science Institute, which I am affiliated with, has created a lot of really awesome tutorials very recently explaining about this whole topic in detail, so I can send that to anyone. But just trust me that if you have something that's really hot and dense, like a star, it will emit in a way that is pretty flat and doesn't really have very much going on. It's pretty boring. We call this a black body spectrum. But on the other hand, if you have something like a light bulb, that is essentially a tube of gas that's being heated up, you'll see a bunch of features in the wavelength of the spectra, which is spectra is literally just a wavelength versus brightness plot. So exactly what I'm showing here. But what you'll see is all these like features, all these big peaks, and that tells you a ton of information. So what exactly it tells you is kind of the basis, relies on the basics of quantum mechanics. Very simply, uh, uh, in atoms, they have energy levels, and these energy levels are quantized. So that just means that the energy difference in any atom will be exactly the same as other atoms. Um, what this means is that when a packet of energy comes in, which is just what a photon is, a single bit of light, if it matches perfectly into that energy, that's the difference in the energy levels, that photon will be absorbed and the electron will be promoted in energy level. This corresponds perfectly every time to essentially the exact same wavelength. And so we're able to map that out. And so if you imagine that you have like a super flat line heading into the thing that has this atom in it, once it comes out the other side, it will be missing that exact type of photon because that photon will have been absorbed by the atom. This is intrinsic to whatever type of atom molecule, whatever it is that you're looking at. And so we're able to map these out. Um, I'll say that emission is just the exact opposite. When the electrons fall back down in energy state, they will get rid of a photon of exactly the same energy that they originally absorbed. So this means that when we look at spectra, so when we look at these lines and we have all these troughs, all these valleys, we're able to relate those to different types of elements. Here, hydrogen. And as this nice little note says, we're able to get a ton of information from this process. So to show this again, imagine this is a planet, not a cloud of gas, but we do the exact same thing in most fields of astronomy. You have your continuous source behind, so it's this nice flat line, and then it goes through this thing where all these different lines are absorbed, and then it comes out the other side with these features in them. And yeah, this is how astronomers figure out what everything in the universe is made out of. It all relies on quite thankless work that's being done by a lot of amazing lab physicists, lab astronomers, where they map the spectra of all these different atoms and elements. And it gets pretty complex, as I'll show in a little while. But so if we've taken our observation of an exoplanet where we take this spectra and we look at it, what do we see? Well, this, for example, is a simulated transmission spectrum of what Earth would look like. So if there was an alien super far away, watched the Earth go in front of the sun and did this technique, this is what they theoretically would see. So you see a lot of things that you would probably expect, things like carbon dioxide and water and methane, a lot of things that we associate with life on Earth. And this looks pretty perfect. It seems like, okay, using this technique, we should be able to figure out what everything is made out of. The reality gets quite a bit more complex. Here is a real data plot. So this is made by a colleague of mine, where these little black dots are the actual data that we get. So if you ignore this line in the background for a moment, if you do this transit spectroscopy technique, you will just get a bunch of dots. So then what we have to do is we build models of atmospheres, taking into account a lot of different physics and things, and we match models to observations, and that tells us all of these different things that we could find. So in this plot, labeled is sodium and potassium lines, and then a whole bunch of water. We see a lot of water. Water is very common, luckily, probably. So great. We now have our transmission spectra. Sorry if I went through that kind of fast, but we now have all this data. So what can we learn from this data? Well, the answer is a whole lot, which is why I am really excited about this field. So to start out with, this is some real data. I am very fond of this plot because this plot was actually made by my thesis advisor as part of the longest ever Hubble Space Telescope proposal. in this proposal, my advisor looked at a bunch of exoplanets in order and was kind of wanted to see what you could see and what you couldn't see, honestly, simply as that. Um, we're kind of in the stage of exoplanet atmospheres where we don't know of very many of them yet. We know of 4,500 exoplanets, but we have seen molecules or atoms in less than 100 of them because this technique is very small signals. So honestly, a lot of what we're doing in exoplanet atmospheres right now is we're just trying to see the similarities, the differences, all these sorts of things, and compare them to each other. Because essentially the idea is that we need a baseline if we want to see anything weird. So this is, it's actually the same lines I was pointing out on the last plot. So you can see that there's this sodium and potassium features that you kind of see in some planets, but other ones like this WASP-12 planet, you don't see at all. That's due to the presence of clouds, which is very frustrating for us. Clouds in the atmosphere of other planets, not in our atmosphere. This was taken from space. But then you see a bunch of water, like we were talking about before. So this seems, again, relatively simple. The data is a little bit messier, but it seems like we can fit models. But like everything, it gets a little bit more complex once you get into the details of things. So before, the elements that I was showing are very simple. The elements where I was showing the absorption spectra. In reality, especially when it comes to things like molecules, which are a lot more complex than single atoms, the types of features that you see get a lot crazier. So you can see, for example, so this water feature right here, you can see corresponds kind of to these like peaks that you're seeing here. But then there's a bunch of other things. There's some weird things like this titanium oxide, which isn't really something that you think about on Earth, but we see in a lot of very hot planets. You see things like methane, water, hydrogen gas, lots of different things. And so this transmission spectra that you see here should actually be a combination of all of these lines that's present at any given time. So this gets really complex, really fast. And so as fast as we want to observe things, we also need people who do modeling to explain what it is that we're seeing. So this is something that's currently being funded quite a bit, and it's kind of holding the field hostage at the moment. But with the few things that we can determine, there's a few really exciting things that we can do. One thing that my group in particular really focuses on is planet formation. So I don't want to get into all the details of planet formation. Again, take my word for it, that when planets form, you have a sun, like a star, form in the middle, and then you get this big disk that's full of gas and dust and rocks that happens all around the outside. That's what happens after a star is formed, but before planets have formed. So thinking about it really simply, as you go away from something that's hot, it gets cooler and cooler. And so at some point, you can imagine that you get to the point where, for example, closer into the star, water would be hot, and so it would be in gas phase. But outside of this point, things would be really cold, and so it would be in like snow or rock or ice. And so this is something that we call a frost line or a snow line or an ice line, really whatever cold thing you want to call it. And this is kind of the basis of our planet formation theory. The simplest way, and this is honestly my favorite way to think about it, is if you think of icy things, they're pretty sticky. And so outside of the snow line where things are full of ice, things will coalesce really quickly. They'll get big pretty fast because you'll get big rock chunks that are cold sticking together. And this will make it so that gas giants can form and further out ice giants can form, these really large planets. While interior to the snow line, when everything is just kind of rock, it just kind of has to like crumble together. That's a lot slower. And so you get your terrestrial planets. And so this fits basically perfectly with what we see in the solar system, right? We have our internal planets like Earth and Venus. And then as you go out, you get to Jupiter and Neptune and all these fun things. So perfect. Seems like we have planet formation figured out. But like everything, that is not the case. Things always get more complex. And so something that happened when we discovered all of these types of exoplanets is that we started finding a lot of planets that aren't like anything we see in the solar system. They are completely different. And so a really popular type of these are called hot Jupiters. 51 Peg, the first exoplanet, was a hot Jupiter. And so these are planets that are giant, but they're in very close in orbits. Like they're flying around their stars at like they'll orbit their entire year will be like 4 days or less. So very fast, very warm. But this doesn't fit at all with our planet formation theory. Our idea is that the gas giants should be like really far out, way far away, orbiting on long time scales. So what's going on? The answer is we don't know. We hadn't really thought about this idea beforehand, but we're trying to figure it out. And so one of the ways we're trying to do this, one of the dominant theories about this is that essentially over time planets will migrate inwards. So there'll be, other big planets will like either like run into them or come close by, will scatter them inwards, and that will cause them to move towards their star. And so like a really simple way that we can figure out if it formed either outside of that thing, the snow line that I was mentioning, or inside, um, is the carbon to oxygen ratio. So again, the specifics are not important. They're pretty boring. But the way that it works out is that you will get a very specific ratio if it formed inside or outside. So my group currently has time on both the Hubble Space Telescope and the upcoming James Webb Space Telescope to observe these types of ratios and see if we can figure out how these planets formed. So that's one kind of idea. The second sort of idea, I'm gonna go through this one kind of quickly, is that just another thing that we found when we were looking at these populations of exoplanets is we found that there's this weird peaked thing if you look at planet size versus number of planets, where we see a lot of planets kind of in this like just over one Earth radius, and then it goes down to nothing or kind of nothing, and then it rises up again once you get to a little bit larger. This is called the radius valley, and we now think that this is due to some planets that we very creatively called super Earths and sub Neptunes, depending on, so this is the sub Neptunes, this is the super Earths, and they're just either slightly larger than Earth or slightly smaller than Neptune. And so this type of like two peaked distribution is really weird. Like if you look at the size of stars, it's pretty flat, like as you increase in size. And so we think this is bizarre. Something must be going on here. And so I think this is a really cool thing because it's one of the really fun things about exoplanets is that we're able to use ideas we learned in the solar system to think about things in exoplanets and vice versa. And so what I'm showing here on the left is actually Mars. So Mars, we know, lost its atmosphere. It used to have this big, beautiful atmosphere, and then it doesn't anymore, right? This is the whole idea that we think that there might have been liquid water on the surface, entire oceans and lakes, but that is no longer the case. And this is basically due to an idea that we just call atmospheric loss. This is basically the idea that as you have a bunch of really high energy stuff coming off of the sun, it goes and hits the atmosphere and just strips it off. And we have now thought that, okay, maybe this is what's going on with these exoplanets we see, because essentially the difference as you go from like a Neptune to an Earth is just the amount of atmosphere. There's some other things slightly, but that's the most important difference. And so we think, oh, okay, it might be just the same idea. And so some people are looking at this. This is just essentially some stuff that's leaving the planet that we can see because it's traveling quite fast. It's traveling at like 50 kilometers per second. So yeah, this is another thing that's currently being looked at. I don't want to talk about this too much because I know another amazing exoplanet grad student, Michaela, gave a talk not too long ago on this topic. But just as a quick overview, I can talk about in more detail if anyone's interested. Biosignatures. So this is the idea that if life is present on a planet, we should be able to see that through things in the atmosphere. The presence of this thing that we call the vegetation jump, which is the presence of plants, or having a specific atom that's only created by biotic processes, etc. And this even goes further. There are things called technosignatures, which is the idea that, oh, maybe there's things that would only technology would give off, like heat from like mechanical things, or even like global warming. So yeah, I can talk about that in more detail if anyone's interested, but I will kind of move on to that. So this is the science that's going on in exoplanet atmospheres right now and kind of all of exoplanets. But the future is very, very exciting in this field. So I'm gonna play a little video while I talk about this thing. This thing that is all I've been thinking about for basically my entire life in astronomy. This is the James Webb Space Telescope, which is NASA's next large space telescope. The big joke on this is that it's been basically soon going to launch forever. I believe the first launch date was in 2006, and it has not launched yet. Although NASA literally announced last week that the official launch date is December 18th of this year. So what is this telescope? To give you a sense of scale, the thing that's opening up right now, which is the sun shield, is the size of a tennis court. So this thing is large. It is an infrared telescope. So a lot of the stuff I've been talking about, and a lot of the things that you think about when you think about regular telescopes is in the optical range. So it's the range that we see in. But this telescope, on the other hand, is seeing in longer wavelengths. And that's really sensitive to things like heat. So what this massive sun shield is doing is it is blocking the solar radiation from the sun to allow this telescope to cool to like a few degrees Kelvin. Basically absolute zero. Another part of this is that it is not going to be in Earth's orbit. It is going to something that we call L2, which is a Lagrange point. You can kind of just think of this as a gravitational well. If things can sit in orbit here, but it's far away. You can't just go and see it in orbit like you could something like Hubble. And this telescope, the promise is that it's going to revolutionize our view of the universe. It's going to see out farther, it's going to see down to smaller signals, it's going to see more than anything we've seen before. That is if nothing fails. The scary thing about things in space is that once we launch them, that's kind of it. We can't really do things to fix them. But the even scarier thing on top of that is that we have had to be very creative in ways to fix many of the telescopes, if not all the telescopes that we have ever launched. We had to literally put a contact lens on the Hubble Space Telescope in order to get it to see right. We had to do the thing I was mentioning with Kepler, where we got its gyroscopes failed, so we had to get the sun to point it. And this is way more complex than any of the things that we've seen before. There are about 350 failure points on JWST, which is terrifying. But assuming everything works, and they've been working such an insanely long time and have put so much effort into this, I am optimistic that everything will work. This will change everything that we understand about the universe. Astronomers right now, a lot of what we're focusing on is preparing for this telescope. Very fortunately, this telescope is being run by the people who are across the street from me at Space Telescope Science Institute. Mission control for this telescope is in that building. We're very sad because they had to remove the cafeteria from there because there was too many electrical signals that were messing with the long distance receivers. But as soon as this launches, this entire area and the rest of the astronomical world will go crazy. We are prepared. The promise is 6 months after launch. So as soon as like next summer, we will be getting data. We will be getting observations that will change everything in a very dramatic sense. So very excited about James Webb. Be on the lookout for that. One of the things I promised early on is that 25% of time, so this is the estimate of how much time a bunch of things would get in the first call for proposals for the James Webb Space Telescope. And this blue section is exoplanets. So we went way above and beyond what we were supposed to get because we had so many great proposals. And those great proposals are going to do some insane science. This is the simulated spectra of a planet called TRAPPIST-1e, which is TRAPPIST is kind of the most exciting nearby system. There are 7 terrestrial planets around a nearby star. And if you look at the scale on this, this is in a unit called ppm, which is parts per million. So the idea is that if you're getting a million photons from the star, we're looking for signal differences at the level of like 100 or 50 or 25 of those. These types of scales are crazy. But this is a terrestrial planet. This is a planet like Earth. We could see Earth-like substances in their atmosphere if everything works as planned. And so we are very, very excited about the future of this. Um, Looking even further into the future, I didn't have time today to talk about ground-based observatories very much. I talked mostly about space-based observatories, but both from the ground and space, there's a lot of really exciting missions that are coming up. A lot of these are already in space. So Hubble is operating, Spitzer died a few years ago, Kepler as well, but TESS is operating, JWST is the next one. And also these ground-based missions are gonna be great. But the big thing that will hopefully be in the news soon is this thing called the decadal survey. So astronomy as a field is small enough. It's really crazy how small this field is, that we're able to literally every 10 years, a committee comes together of astronomers and they say, okay, what do we want this field to do in the next decade? The decadal has been responsible for basically every large telescope that's ever existed. The 1990 decadal, I believe, or the 1980 decadal was responsible for what we call the Great Observatory. So that's Hubble and Spitzer and Chandra and Newton. The 2000 decadal, or it might have been the 1990, 10 years doesn't make that much of a difference, was responsible for the James Webb Space Telescope. The next one was responsible for this telescope that we call W first. It's now called the Nancy Grace Roman Space Telescope. And now, as everyone is well aware of with how last year went, we just entered a new decade. So literally any day now, the report on the next decadal should come out. In fact, it was supposed to come out originally last year. Then it was supposed to come out by late spring, and now they haven't said anything since spring. So it could literally come out any second. And this is kind of terrifying because it's going to set how astronomy is for the foreseeable future. Because a big difference that's kind of happened since telescopes like Hubble is that these large missions have taken longer and longer. Like I mentioned, James Webb was first supposed to launch like before 2010. Now its launch date is 2021. And so these large telescopes that I'm showing here probably won't launch until the 2040s at the earliest, if not the 2050s. But luckily for people like me who like exoplanets, of these 4 missions that were all, so these missions were all proposed to NASA as the next big thing, basically. And of these 4, 3 of them have exoplanets as one of their main goals. This telescope at the bottom, Lynx, is a little bit different. It's an X-ray telescope, and they're kind of off doing their own thing in X-ray world. But the other 3 all have exoplanets as one of their main goals. And of those, these 2, LUVOIR and HABEX, have exoplanets as their main goal. HABEX is literally the habitable exoplanet telescope. So that tells you that that's what they're looking for. And so hopefully once this survey comes out, they will, so the survey comes out, then it's sent to Congress. Congress then decides what they want to do with this call. They have never rejected it. They've always accepted it at face value. So hopefully the same thing would happen. And so we may have a telescope that would be capable of finding life on another planet within the year. Of course, it won't launch for a long time, but we would know that it might exist. So yeah, so that's kind of a very optimistic look at the next few years. By few years, I mean few decades of exoplanets. And thank you all for listening to me talk for 45 minutes. I'm happy to take any questions.
All right, good job, Natalie. Thank you. Thank you. Did that really, was that 45 minutes? It seemed like it went really fast. Um, a lot of good information there, and I know you had to skip over a lot of stuff because we didn't have time to get into the weeds, but fascinating. You must be having the time of your life
Yes.
studying all these details. So that's great. Thank you for sharing that with us.
Yeah,
Um,
thank you.
Questions from the floor. Somebody drew a picture. Let's see. Jane Marie is showing a picture. I don't know if you can see it. Natalie, stop sharing your screen, please,
Sure.
and
Mhm.
then folks can see. Hold that up again. Um, yeah. Um, I don't know if you can. Can everybody see Jane Marie, the
Just
picture that she's
our
holding?
daughter Olive. She's very interested in.
There you go.
All right,
Oh,
you got it. You got it.
Oh, that's great, Olive. Yeah, thank you. That's
Thank you
great.
so much for the talk, Natalie. That was fascinating. Really enjoyed it.
thank you.
Okay. Wow. Let's see. Okay, there is a question from Jay in the chat. How far away is do you mean TRAPPIST system, Jay? Is that what you're referring to?
My spelling's not great.
How far
Yeah,
away is the TRAPPIST? Yeah.
TRAPPIST system is only 40 light years from Earth, which is incredibly close in astronomical terms. It's so close that there are some billionaires who want to send cameras using a system called a solar sail to this system. Um, and if it's the reason people are so excited about it is because it's technically feasible that this is a type of system that humans would be able to visit in theory.
Okay, so that solar sail would be traveling at something substantially less than the speed of light, so it would take a whole lot longer than 40 years to get there. Is there an estimate
Yeah.
for transit time?
So for the good thing about solar sails is so a great thing about space is that there is no deceleration. You're going through space, you're just flying, you're only accelerating. And so the idea with the solar sail is so photons, all light has a force behind it. And so you basically get a really small payload. So the idea would be to send just one camera essentially, get a massive sail that's able to get a ton of the force from the sun, and it would be able to I believe the highest estimate was about 30% the speed of light. So it would be able to get there in a few generations, which I know sounds like a long time. But when cosmologists are dealing on with terms of billions of years, it really seems like a doable thing.
So 40 divided by zero point 0.3 would be about 120 years, right?
Yeah,
Did I do that right?
approximately.
Yeah,
Yeah, you have
okay.
to get in the acceleration time, which takes a few decades, but
So
order 200.
150 years or 200 years. Okay. Yeah. So the people who launched that telescope will not be around to see the result. Okay, a couple more questions. Let's see. Gary says, "Oh, comment. I don't remember ever learning so much in 45 minutes. Thank you very much."
Thank you.
That's
Very
great, Gary.
kind.
Thanks, Gary. And Annika wants to know what is the most effective method for finding terrestrial exoplanets?
Great question. So it kind of depends on, like I'm saying, which one of these missions gets funded, because the big thing with finding terrestrial planets is whether you're looking in the transit technique. Okay, so the basic answer is either the transit technique or the radial velocity technique. That's because even though we may be able to find them with the microlensing, the weird gravitational technique, we don't really care about that because we will never see it again. If we are interested in actually finding them for doing interesting research, then a lot of it comes down to which instruments are being funded faster. At the moment, it looks like probably the transit technique will be better, just because people are a lot more interested in what we call imaging telescopes. So telescopes like Hubble, which can bring back these beautiful images. That's what you're looking at all the time. The what you use to get a radial velocity spectra doesn't return um, anything pretty. It's just lines. So the public tends to want imaging telescopes. And so my bet is on the transit technique. We've already found some terrestrial planets with the transit technique, but only around pretty nearby stars.
Okay, Steve has a question, but before we get to that, I want to jump to Brad's comment to say that Annika and Grace, who are both present tonight, are founding members of the Hyla Astronomy Club. So
Oh, that's amazing.
welcome to the Hyla Astronomy Club. Looking forward to working with you at Battle Point. Okay, back to Steve's question. What instruments are on the Webb for detecting exoplanets? Does it include holographic aperture masking?
Oh, it does not include aperture masking as far as I'm aware. The main telescopes are spectrographs. So there are four main instruments on the James Webb Space Telescope. There is their nearest, it's not important. There's a bunch of different things because the big thing with different types of astronomy is that they need different resolutions. So you need things all the way from like low resolution, which is like kind of what we do with exoplanets. We don't need really high what we call spatial resolution, which is like how you get very beautiful images. We don't need that. We need quite sparse resolution because you can get a lot more pure information from it. And so the objects on the James Webb Space Telescope will be able to observe from the near infrared. So it will actually overlap with the Hubble Space Telescope a little bit, which is really important actually. And it will go all the way out to the mid infrared, which is all the way out to something like I believe the furthest out spectrograph goes out to 25 microns. For reference, the entirety of the Hubble Space Telescope's like seeing range is only about 2 microns. So we're going to be able to see like 15 times larger wavelength range than we'd be able to see before. Of that, the most interesting things are all relatively near infrared because stuff gets weird when you try to see far out in the infrared. You're no longer having cameras, you're having kind of specific detectors. But yeah, as far as like aperture masking and stuff, I think that's a technique that's more often used ground-based things where you can kind of have more specific use cases.
And mentioning, since you mentioned the JWST, before I forget, I want to mention that BPAA is collaborating with KittyMew, and on November 20th, we're going to have a special event at KittyMew uh, in anticipation of the launch of the JWST. So mark your calendars for November 20th. I think it's a Saturday. Um, we're going to have telescopes there. We're going to have volunteers speaking about telescopes and speaking about the James Webb Telescope in particular. And weather permitting, we'll have telescopes set up for viewing the sun during the daytime. And we may even have a star party from the rooftop there at KittyMew. So mark your calendars, kids. It should be fun. Okay, we have another question. Somebody says Como. I don't know that name. We may have missed it, but is there an exoplanet that appears to be very similar to Earth?
So unfortunately, no. This is kind of the holy grail of the field right now. This is what everyone's trying to figure out. So what we have as far as, because we do know of terrestrial planets. So we know of planets that are kind of like the Earth in that they are rocky. They probably don't have very much of an extended atmosphere like a gas giant does. But we have nothing that has an atmosphere still. So you can think of the planets like Earth that we know of to be much more similar to like a Mercury than an Earth. And that it's basically a bare rock that has had all of its atmosphere destroyed, essentially. But assuming that the James Webb Space Telescope delivers as promised, it is possible that one of the TRAPPIST planets, which is the planets I was mentioning, would be able to be Earth-like. So they are quite a bit near in to their host star, and that's because I didn't even talk about stellar types, but stars, as they get warmer, they get larger. And so the place that we call like habitable moves out a lot further. But the TRAPPIST star is an M star, which is a really, really low mass star. I believe it's less than 10% the size of the sun. And so even though these planets would be similar in a lot of ways, they would have a very different environment in that they, I believe the longest TRAPPIST system's year is about 30 days. So they're still going pretty fast around their host star.
Okay. And let's see. Will would like to know what the Webb telescope is made of.
Oh, good question. I am not an instrumentationalist, so this will be testing my knowledge. I believe so. There's kind of the mirror, and which is actually segmented, and then there is the sun shield. And so I think the sun shield is made of. We get into this weird kind of regime when it comes to things like this, where they're proprietary, so the public isn't allowed to know about them because they're being used also for military activities. This happened with a instrument that launched a few years ago called the Parker Solar Probe, where the Parker Solar Probe went into the sun, basically. And the requirements for that, the heat shielding on that is so extreme that the military wanted to use it. So we aren't allowed to know what it's made out of. So I'm not sure if we know what the sun shield is made out of, but it's usually those types of things are made out of like aluminum type materials that can be very thin metals that can reflect a lot of heat. As far as the mirrors themselves, they're gold coated. So you can see that in all the images of them. And they're essentially mirrors that are covered with a layer of gold coating. And yeah, the kind of interesting thing about it is that if you think about a traditional telescope, you have a single lens, right? Just a big circle filled with that you can get all your light in. And the James Webb Space Telescope is too large for that. So it's actually segmented. It's a bunch of hexagons that they stick together. And that makes it so that single, because it's really hard to make a lens really big and really perfect. And so they make basically small ones that they stick together so that if there's something wrong with one of them, it doesn't affect the entire thing. Hopefully that kind of answered your question.
And I think those individual hexagonal shaped mirrors can be, um, do they have actuators on the back so they can be fine tuned to make sure that
Yeah.
their alignment is correct?
Yeah, they absolutely do. So the first, I kind of mentioned this, but the first 6 months of the project, so after launch, well, the first about month, it's going to take to get to its point at L2. But after that, the next 5 months are just for commissioning. So the entire thing is that they're going to be focusing the telescope and slightly changing the mirrors, and so that they can get the most perfect resolution that they possibly can. A professor of mine, Laurent Poyot, is actually the head of that effort. It gets pretty complex.
Natalie, do you know, are the mirrors behind the gold plating, are they made of glass or are they made of some other material? Do you know?
I believe they are coated in a metal. But honestly, I don't get to do very much with actual hardware, so I'm not sure.
Okay. Steve Rule, do you happen to know what the substrate is on those mirrors?
Not definitely. I would think that they're some sort of carbon fiber, and then that's ground and to the surface, and then blasted with the gold.
That makes sense. Carbon fiber is very light but very strong and dimensionally quite stable. Yeah. Okay. Let's see. We've got more questions. Could astrometry hold promise for finding more exoplanets in the future?
Oh, good question. Yeah, so astrometry is a method that I didn't mention previously because it hasn't really been used much to this point. But there's a mission right now called Gaia, which is this amazing, stunning resolution astrometry mission. And there are actually some planets that the Gaia team has said that they have found. They have not been confirmed, but very simply, astrometry is literally following the position on the night sky of specific objects. So you just find the location. And so the idea is kind of similar to the radial velocity technique, that you would see kind of spiral motions as an orbit is happening, and you'd be able to use that to find planets. maybe one has been detected using this method so far, but not a lot. But the Gaia team and the teams that are going to come in the next Gaia evolution are very excited about the potential for that. So yes,
The Gaia mission is fascinating in its own right.
absolutely.
Yeah, it's a mission of the European Space Agency, ESA, and if you go to their website and just read about the Gaia mission, it was planned to do some amazing things, and now that it's in service, it has really already sort of revolutionized our understanding of a lot of things, in particular the dynamics of the Milky Way galaxy. It's just fascinating what they're finding.
Yeah.
So yeah, check that out if you want a good read. Um, let's see. We have another question. Oh, you mentioned 350 failure points on the James Webb, and Jane Marie wants to know which one is the biggest risk.
Ooh, good question. So the biggest scary thing is that sun shield that I was showing that was deploying. So it's this big thing. The scary thing with James Webb is that, so if you think about like a rocket, right? It's like this cylinder, and so everything has to get wrapped up in order for the actual telescope to launch. And then once it gets up, it has to deploy. And so the sun shield, actually, when I was at JPL, there was a team that was working on the best possible way to wrap the sun shield up so that nothing would get caught, nothing would get like ripped, because if something rips on the sun shield, it's kind of game over. And I don't know if you guys caught it when I was showing the video, but the sun shield is actually 5 layers. So there's 5 separate layers of sun shield, and all of those kind of need to be perfect for this to work. And so a lot of the failure points are in the sun shield itself. The telescope you may have been able to see was kind of just one main mirror with most of the hexagons, and then just these 2 panels had to come out, and that's pretty safe. We've done things like that before, but the sun shield is completely new technology. They had to make entirely new materials, entirely new everything for this.
Yeah.
And so the big fear is that the sun shield will not properly deploy into its right shape, or something will catch. And if that happens, the telescope will heat up until it's too hot to see to some specific wavelengths. Some of its instruments will still work. They made sure of that because they don't want the entire telescope to fail if something happens to the sun shield, but kind of the most exciting capabilities would not work.
Yeah, nobody's ever failed on any large object deployment in the spacecraft before.
Yeah.
I
Space,
detect a
we
little
have a
bit
lot
of
of
sarcasm there, Steve.
Yeah, anytime you deploy solar panels or anything like that, I mean, if you go back to like Skylab, it deployed wrong. Hubble, it deployed wrong. It's tough to deploy very light things that are very far, that are very extended long ways. As someone who worked in that field, I can tell you that.
First-hand experience.
Yeah.
Yeah. I read somewhere that when when the James Webb was first thought of, and when they did the initial planning and arrived at the basic design for it, SpaceX wasn't yet in existence, and the big rockets that SpaceX now has were not. Nobody knew that those rockets would be available, and so they had to design the James Webb to fit in the largest rocket that was then available, which is the Ariane space rocket. Um, and it's because of the limited size of that rocket, the limited payload volume of that rocket, that they had to come up with this folding mechanism and get the telescope packed into that rocket. Now, if they had known that SpaceX would have these big rockets available, I think that James Webb would have ended up looking quite different, at least in
absolutely.
its folded configuration.
Yeah, I worked on a project where the from when we started to when it launched was over 10 years, and it was originally supposed to go up in the shuttle, and it got pushed off to a Titan 3C. I mean, the Hubble went up in the shuttle, but it stayed in the high bay at Lockheed for like 3 or 4 years. I mean, I saw it in the high bay, so yeah, there's always delays.
Okay, let's see. Well, there's a last question here. Jay wants to know, is there a way to tell a color of an exoplanet?
Um, Yeah. So color is kind of an odd thing in that when the way we think of color, we think of the optical range. So what we're talking about. So around 600 nanometers is like the color red, and around like 400 nanometers is like a bluish purple color. And so yeah, when we look at things in the optical, it has a color that you could think of. A lot of planets, as you would see them, are actually more like a blackish color because they absorb a lot of light. You can kind of, a lot of these hot Jupiter type planets that we're talking about. Um, but if you're thinking of more like a terrestrial type planet, yeah, then yeah, they absolutely have a color. Once you get out of the visible wavelength range, the idea of a color kind of loses meaning. Like it's something in the infrared has a glow due to a heat rather than a traditional color. But we map these to fake colors to make things look pretty a lot of the time.
False color is a great technique.
Absolutely.
Okay, I don't see any more questions in the chat. I don't see any raised hands, but what a great sequence of questions we've been getting. Thank you so much, everybody. Um, and any last words, Natalie, that you want to share with us?
Um, Not that I can think of. Thank you
Okay.
all for giving me an opportunity to speak to you today.
Well, thank you for coming. This is great. Folks, if you're familiar with the reactions button on the bottom menu of Zoom, you can give Natalie a clapping hands. Uh, yeah, let's see some clapping hands or thumbs up if you want. Yeah,
Thank
thanks
you.
so much, Natalie. This is great. This is great.
Thank
Well,
you.
okay. If Okay, there are some kudos coming in on the chat. So when I close the meeting, the chat file will be saved, so I'll be able to share that with you, Natalie, and you can see all the thanks that everybody's putting there. Um, okay, well that concludes our talk for tonight. So until then, everybody, thanks so much for coming. Appreciate your interest in BattlePoint Astronomical Association and our programming. And thanks again, Natalie. So glad you could join us. We hope to see you again.
For
When you
sure.
get your
Thank you.
when you get your PhD,
Yeah,
come online and we'll have a celebration.
yeah. Natalie,
Perfect.
you and I did impact cratering studies on computers to get different generations. I actually did that many years ago also for
Awesome. That's great.
did some experiments at the NASA Ames vertical gun. So
Oh,
that was,
cool.
yeah, yeah, that's really cool.
Thank you.
Okay, great. Well, I think at this point I'm going to stop the recording